Hello, welcome to another practice problem. We're going to do problem 8.13 out of the textbook. It says here, cross-sectional dimensions of the beam are shown. Part A states, if the bending stress at point K is 35 megapascals in tension, determine the bending stress at point H. We need to state whether the stress is in tension or compression. And part B states, if the allowable bending stress is 165 megapascals, determine the magnitude of the maximum bending moment, M sub z, that can be supported by the beam. So part A, right, says if the bending stress at point K is given, determine the bending stress at point H. So looking at our diagram here, our sub z is 90 millimeters, our K is 90 millimeters away from our Z, and H is this other distance here, right? So what's that, 175. So we'll say this distance here is 175 millimeters. Okay, so for part A, what we can do is just build a simple relation. We can say if the known information, which is the bending stress at A, is a certain distance away from our neutral axis, right, which is our y sub h, well, we can set that equal to the bending stress at K. I'm sorry, that's the unknown. I apologize. These are the sigma sub h is unknown. And we can set that to our known value sigma sub K multiplied to our y value for K. So now all these values are known. This is known, this is known, this is known. We just need to solve for this. So just through algebra, we can get our sigma sub h is going to equal sigma sub K multiplied to the y value of h divided by the y value of K. Okay, so sigma sub h then equals the given value was sigma sub K, which was 35 megapascals in tension. So 35 megapascals. And we have, from our neutral axis, right? Our neutral axis, both values are going down from our neutral axis. And so there'll be a negative, we'll say negative 175 millimeters divided by a negative 90 millimeters. And solving this out, we should be able to get sigma sub h equals 68.056 megapascals, and it's in tension because it's a positive value, so sigma sub h equals approximately 68.1 megapascals in tension. And part 1 done, or part A. So for part B, I've already solved for the moment of inertia here. That so it should be something that you are familiar with doing. So this is our moment of inertia about the z-axis, right? So I'm going to kind of skip that part and we'll just jump into part B. So part B, if the allowable bending stress is 165 megapascals, what is the moment, right? What's the maximum moment? So knowing our formula, right, is going to equal, or our bending stress, right, is going to equal our m multiplied to y divided by I, right? So solving this for m, you should get sigma sub b multiplied to I divided by y, and that will equal our moment. So sigma given is 165 megapascals. So megapascal is newtons over millimeters squared, right? Multiply that to our moment of inertia, which if you can see here from what I did, all these values up here, if you want to check my values, go ahead and pause the video if you need to and check all these values, but these are all done in millimeters, right? So now multiply sigma to our I value, which is in millimeters, millimeters to the fourth. Millimeters to the fourth. There's an error. 4022386667 millimeters to the fourth. And divide this by our y value, right? What's our y value? Right? So good question right here. We're going to pause for just a moment and reanalyze what is our y value. If we're going to have our maximum bending stress occurs at this maximum distance away, which happens to be at point H, right? So the maximum distance away from our neutral axis, which is 175 millimeters. Okay? So we plug 175 millimeters. Let me rewrite that and make it look nice. 175 millimeters. And this will equal our moment. Okay? So you should plug the values in, use your electric brains, and you should get a value that should say 379253600 Newton millimeters. Right? Which equals 379 kilonewton meters. And that will be our moment, maximum moment. And that's part B.